Continuing our study of RSA, we're moving on to security. What we'd like for RSA security is that if I give you the modulus and an encryption exponent, and then I also give you the result of applying this function f to some point x, and then I ask you to recover x, then you should find that to be difficult. So we call this the inversion problem. Someone picks x at random, let's say, raises x to the eth power and gives you y. They also give you n and e, and given all of those three, you are being challenged to recover x. Note that mathematically there's a unique x satisfying this equation. The question is, can you find it when n is quite large? So as indicated, security would like this problem to be hard, but let's see how hard it appears to be by effectively trying to solve it. Before we do that, let's formalize it. So as usual, we can have a game and advantage version, and this formalization tells us something that wasn't visible earlier. When we speak of hardness, of what object is the hardness, to what does it apply? And the answer is to an RSA generator. So we take some RSA generator, and it could be the example one we saw earlier or something else, and we associated to that a one-wayness game. In that game, procedure initialize runs the generator, which gives it this 5-tuple, modulus 2 primes and encryption and decryption exponents. Now it picks a random point in Zn star, call it x, and applies RSA to that, so it raises x to the eth power to get y. What it returns to the adversary is the modulus n encryption exponent e and the point y. It does not return p, q, or d. There's no other exported oracles. The adversary has to trundle along, and its goal is to find x. Eventually it outputs some x prime, finalize takes that, and sees if it got it right. Is x prime equal to x? If so, it returns true, otherwise it returns false. So the adversary may or may not win this game. If you run an adversary, we can call it I for inverter with this game, and if it returns true, then it wins the game, and that has some probability of happening, and that probably is the advantage of this adversary. OW for one way is the name of the metric. Here the object whose security we are measuring is the generator, and I is the adversary. So let's try to solve this problem. So imagine you are an adversary playing such a game. You've just been handed an EY, and you're trying to find X. What could we do to do that? So let's apply all the math we know. The first thing I observe is that it's actually easy to compute X. I know that X is what we call F inverse of Y, and it's obtained by raising Y to the dth power mod n. That's the basic property of RSA, that if x to the e is y, then y to the d is x. Okay, but that doesn't quite solve the problem for us computationally, because in our inputs here, there was no d. We were not given d. But still, it's progress, because what that tells us is if I can find d, then I'm done. Then I've broken RSA, I've solved the one-wayness problem. So let's go look for this d. But this looks fairly easy, because if you remember, there was actually a formula for d. d was the inverse of e modulo phi of n. In the group z star phi of n, this point e has an inverse, and d is exactly that. Furthermore, we have an algorithm to compute it. The mod inverse algorithm would return d. So aren't we done? Can we apply that algorithm and get d? The difficulty is that that algorithm takes input not just e, but also phi of n. It needs to know modulo what you want the inverse, otherwise it can't function. Okay, that means I'm not there yet, but I seem to be making progress. I can now reach my goal of finding x if I have phi of n, because then I can run mod inverse and get d, and then raise y to the dth power. So let's try to compute phi of n. We notice as we are going through these simplifications that less and less about the input is relevant. So over here, we were worried about NE and Y. Once we come here, we no longer worry about Y. We're done with that. Once we come here, we don't even care what E is. All we're concerned is with something concerning N. There's a formula for phi of n. So again, it looks like we are in pretty good shape. We know that phi of n, as per prior slides, is p minus 1 times q minus 1. So I can easily compute phi of n from this. What's the catch? No one gave me the primes p and q. Remember, p times q is n, but although that mathematically given n uniquely defines p and q, I wasn't handed them. Okay, so I have to find p and q. And that brings us to the last problem, and that's factoring. How do I take the modulus n and find p and q? And that's the part where we kind of hit the end of the road, because factoring is not going to be that simple. So what is the factoring problem? Given a number n, which let's say in this case you know is the product of two primes, find those primes. And what we saw just now is if you can factor, you can invert RSA. It may be worth noting that the converse is not necessarily true. So there may be ways to invert RSA that don't involve factoring and don't go through that particular chain of reasoning we saw on the last slide. But there isn't anything like that particularly known. So from a practical perspective, we focus on factoring. So let's try to factor. Well, it's not hard to do in principle. If I give you a number n to factor, you have an obvious method, trial division. Try all possible divisors starting from 2. You can stop at the square root of n because if there's any non-trivial divisor, there's one smaller than that. Test each divisor I to see if it divides n by computing n mod I. If that's 0, then I divides n, and you have a factor. Since we know that n is the product of two primes, one of those factors is p and the other one is simply n divided by that. So we would be done. And how long does this algorithm take? Well, about the square root of n elementary operations, which if you write it in exponential form looks like this. This e, not to be confused with the RSA encryption exponent, is the base of natural logs, 2.7. And so it's e to the 1/2 of the natural log of n. You can, again, go on the internet and do this. There are integer factorization calculators. So we could enter numbers in there and try to factor them, and it'll do that. 851 is 23 times 37. So it did that pretty fast, right? But what is the catch is that this is not going to keep up too long. As numbers get bigger and bigger, this is going to get smaller and smaller. It's going to take more and more time. I don't know how many it will allow me to enter. Okay, it did that one. Found a small factor, got a little lucky. But I'm not seeing here a limitation written, but obviously there's one somewhere. Okay. So, so here we are then. We have an algorithm to factor, but it's slow. We've encountered this before with discrete logs. From a perspective of security, this is good news. We want factoring to be slow, to have security. But we better be careful with regard to whether it's really as difficult to factor as the last slide indicates. And indeed, the answer is that there are way better algorithms out there. Nonetheless, these algorithms are not fast enough to be practical on numbers that are, say, 1,000 bits long. The first non-trivial factoring algorithm was called the quadratic sieve. Its running time looks something like this. To factor a number n, it takes time about 2.7 or e to the power the square root of the natural log of n. So this is roughly the bit length of n, but then taken in a square root. And then other stuff. And the number field sieve, the current best algorithm, replaces the square root of the cube root, so it's way faster. These square and cube roots make really, really big differences compared to this. So for example, consider that n is, say, around 2 to the power 256. Well, then maybe this thing is about 256. and this is 2 to the power 1, e to the power 128, very, very roughly. But over here, when you take the log of n, which is 256, and take its square root, it's really quite small. And its cube root is even smaller. So you can see that there are massive improvements indicated by these algorithms. In any case, we also know that these asymptotic running times are not enough to be sure how hard it is in practice to actually factor some specific number. So people run experiments, and they've often taken the form of challenges. So RSA Corporation posts challenges and offers dollar amounts, and the numbers have varying bit length, and you can try to factor them and get some money. So we can see that back in the early 90s, they were able to factor 400-bit numbers using the quadratic sieve. The reason that was interesting at the time was that the quadratic sieve had just been introduced. RSA didn't know when they posted this that this new algorithm would come and factor them. By the mid-90s, the number field sieve, our third algorithm, was being applied to even bigger numbers. Now, even up to this point, the general standard in the industry was to use 512-bit RSA moduli, and people thought that was safe enough. Nobody's ever going to factor a 512-bit number. So it was really major news in the late 90s when they did factor a number of around 512 bits. Here, this did not arise from a new algorithm, but from faster, better implementations and distributed computing and all kinds of computational speed-ups. But this led to a complete rethinking of the size of moduli needed for security. And after that, people have recommended a minimum of 1024. It didn't stop there. By 2009, they were able to factor 768-bit numbers, which is really, really remarkable how far they've got. We can look where they are now. I think my slides may be a bit beyond the time. This thing discusses what's called the RSA Factoring Challenge, which was started by RSA Labs, which was one of the entities that was selling RSA crypto products, and so it was to their advantage to have a strong belief in its security. And one way they got that is by posting these challenges and seeing what people could solve. So it started out slowly, and you can see here, interestingly enough, that in 2007, RSA stopped the challenges. And why did it do that? Well, possibly because it was they were being solved and they were losing money. I don't really know. Anyway, you can see how things went. What's written here is the number of decimal digits, and here's binary digits. So 300 odd binary digits were being factored by the early 90s. And then here are the ones with the quadratic sieve, and it went on. You can see the dollar amounts being paid. It's kind of funny how it actually goes down. This is 17,000, and then here it's dropped to 10,000. But this was the big deal. This was the 512-bit modulus. Oh no, that was up here, and they got 9,000. Huh, less than for 463. Okay, so here 768 was 50K, and that was one. These, I guess, have not been paid out. But what's the record? Right now, they're actually, well, they were able to factor an 829-digit number. Right, that's the current record. It's really quite amazing. So the current wisdom then is that an 80-bit security is what we would like. That means the adversary's time to factor is about 2 to the 80, which seems out of reach by present methods. And that requires a modulus of around 1024 bits, maybe somewhat more. So that's the minimum recommended size. If you want high security, you'd go above. This is just, if you like that video so much and want to watch it again, this is just the pointer to it. So this is a summary of what to remember with regard to security of the RSA function. So it's what's called a trapdoor one-way function. For large enough modulus n properly chosen, it's hard to invert without the trapdoor information D, given only NE and the result Y of applying F to some point X, it's hard to recover X. If you know the trapdoor D, it's easy to recover X. You just raise Y to the Dth power. And in all ways, if you have the modulus and encryption exponent, it's easy to go forward. Now, it turns out that although it looks to be the case, using RSA for encryption is not as obvious as it may seem. So we'll get to that in a